Okay, so today we're going to finish the penalty-based method, and also we're probably going to start the SVM support vector machine. We're using with ADMM, like we apply with application to the big data. So before I go there, have you guys started to talk about the final group projects? Yes. Did you have the first group meeting? Good. All right. So hopefully that thing can be like the topic can be chosen like this week, but then you guys can start to work on it. Okay. So for the penalty-based methods, as I explained in the last time, basically what it does is it adds a penalty. So you have an object function, you want to minimize something, right? You want to minimize either the mean square error, like in the regression problem, or you can minimize the negative log likelihood, right? In case of logistic regression, or some other penalty, like the loss function, we call loss function, right? Some kind of error measurement. So you want to minimize the errors in the object function. Now, in addition to that object function, we append additional penalty, so-called penalty term, the lambda times r beta into the objective function. This lambda is bigger than 0, and r beta is the so-called penalty applied to your parameters. So the usual r beta could be the sum of the absolute value of the parameters, or sum of the square of the parameter. So if you just from the on one hand we want to minimize our loss function. On the other hand, we want to making this is our summation of the parameter. Okay, either in absolute sense or in the square form. We want to minimize it. So the penalty term essentially what it does is try to making this beta not too big. Okay, not too big. We're gonna explain actually today the effect of the beta is actually the shrinkage. Okay, it's actually shrink the beta or the coefficient actually toward to 0. In some cases, it actually to 0, but in other cases, it are shrink toward 0. So this is penalty term compared to the original. If you want to minimize the loss function, it's basically its effect will be the shrinkage effect. We also discussed a little bit about why we want to include the penalty term here. Originally, the penalty term was included for numerical stability. Okay, so people try to making making the solution for this is the regression like more stable, because when your X has a collinearity, in a case like where some columns are highly correlated. Okay, so then the solution, which is X transpose X, may be in the yield condition. Okay, maybe not invertible. So to making that thing to be more stable, we am adding a diagonal term to this X transpose X to making this to be non-singular. So originally, this is people develop things like ridge is for the reason of the numerical stability. But later on, people actually find out the penalty term actually can introduce like additional benefits. The main thing, as I explained last time, is called the variance bias trade-off, right? So if you want to minimize the errors of your estimation from your two parameter, which is mean square error can be written as summation of the variance of the estimation plus the bias of estimation. So this penalty term is in some cases, okay, it actually can you sacrifice a little bit bias. In other words, is your estimation is longer unbiased, but then you can greatly reduce the variance of the estimates. So therefore, make the whole mean square error actually become smaller. So in that case, is beneficial. So that's pretty much that's what we sort of cover about the penalty method from last class. That's a little bit recap. Now, one thing to notice here is since we penalize the beta, right? So if you want to if you want to make it beta, so beta, the scale of beta actually matters, right? So it's, for example, if you have an x, right? If you have an x is in the unit. If the x is some kind of weight, okay, is some kind of weight in the measurement, right? This is the weight measurement. Now, depending on the unit of x, if it is kilogram or gram, okay, then the coefficient we're including the x into the regression, then its coefficient, the value actually going to change, right? Because if you see the x effect to the y is the same, by regressing, see the x is like 1.1 kilogram or is 1010 gram. It depending on what value you use, which unit you use for the x, then the beta coefficient will be different. Because if your x is the kilogram, the x value is going to small, right? So it's actually going to small. So therefore, make your beta is going to be bigger. But when you're using the gram, your x value is going to be big. So correspondingly, the beta value has to be go down. It's like 1,000 times less in order for the overall x effect, the weight effect to be the same, right? To be the same. So therefore, if you just including the raw value of x into the regression, when you penalize it, right? Because what is the SSE plus like lambda times say beta 1 squared, right? Plus like beta p squared. So if you're using the lasso ridge penalty, then see the beta 1 is corresponding to the weights. Then in this case, if you're using the kilogram as unit, you have a very large coefficient. If you're using the gram, you have a small coefficient. Then their effect to the beta is going to be different. Okay, it's going to be different. So in this case is about we don't want that happen. Okay, we don't want that happen. We want our the so like penalization on the beta should be like more skill free. So therefore, for the penalized method, typically we have to do so-called variable standardization. Okay, we need to standardize the variable into some standard form. So usually, typically, we just do is so-called normalization by standardization by subtract the mean of then for the xij for the xj, right? We just basically this vector with minus its mean then divided by its sigma. Okay, so to make it is the mean 0 and the variance is equal to 1. So in this is what I call variable standardization. The main purpose is to first making your variable, make your coefficient to be scale free, right? So in this case, if you do a standardization, no matter using the kilogram or gram with a different unit, doesn't matter because we eventually we're going to standardize it, right, to the same value or same scale. Second of all, also making the different variable are comparable coefficient. Right? Otherwise, if you don't standardize it, then some using kilogram, some using like a meter, then they may for some variable they may have very big just intrinsically has big beta. Some other variable have small beta. So therefore, when you penalize it, then you're going to have then the big beta may dominate the penalization term, right? So essentially, if one beta dominates the penalty, that essentially means we don't have the penalty on other covariates. Well, other x will be like inactive, right? So in that case, it's undesirable. So therefore, the standardization basically solve two problems. One is unit free, scale free, right? To making the second to making the different x, okay, different covariates are comparable from each other. So that's like the two reasons why you want to standardize it. So this is the step. So like we need to do before you're feeding the model. Now, if you standardize it, once you're making the variable like each covariance x to be mean 0, and you can also standardize y to be mean 0. Once you do this standardization, then in the regression problem, intercept basically is gone, right? So therefore, when we talk about this is a penalty, we're not really penalize the intercept, but more penalize on the beta coefficient for each x. Okay, so this is another thing. So penalization, this is R beta does not include intercept. So that's this is one another thing. One more thing I want to talk a little bit about the standardization is, so usually when you fit in the model, okay, you are having you all have a training data and you all have a test data. Okay. So when you standardize a variable, when you're making this is your variable to be mean 0 and also the variance is 1, you're gonna subtract the mean and divide it by the standard error of the variable, right? That two values are based on your training data. Okay, that two variables based on training data. So in another word, that's when you do xj minus x bar divided by sigma. So these two values are calculated from the training sample. When you do the testing, okay, your test sample should subtract the same two values. So when you train the model, you not only you just need to having your beta coefficient to be available. For each variable, you should have its normal or the standardization variable, okay, or the parameter like x bar and sigma for each x. You should also keep that in order for you to when you do the testing or do the prediction, because those essentially become part of your the parameters, that part of parameters. They just fix. These are fixed parameters. You don't need to estimate them, but they are part of the model. Okay, so keep that in mind when you want to apply this like lasso or ridge in the future. If you want to write your own program. Okay, so this is variable standardization. Any question on this? Okay, so the variable standardization, if this is for like the first time you heard this concept, it can be confusing. But if you think a little bit more about it, actually making intuitive sense. Now let's look at the ridge regression. Okay, so what it does. Then once we're still going to start with something like a simple ridge regression is pretty simple to work with. Then we're going to extend it to like L1, okay, to the so-called lasso regression. So ridge regression, what it does is we're going to penalize the sum of square by adding a term, the penalty term. The penalty term basically is lambda times summation of beta j squared. This is not pi. This is actually p. Okay, so somehow some reason this is it must be the text issue when I type it is I type it wrong. So this is on the penalty term. Okay, make a correction here. Is a summation j from 1 to p. Okay, beta j squared. The first term summation over all the summation over I, right? That I is for all the sample. Your summation over all the sample. For example, you're going to do yi minus beta 0 minus this is summation j from 1 to p xij beta j. So this is your model. This is basically the whole thing here. This is your SSE, right? Sum of the square of errors. Plus penalty term will be lambda times summation of beta j squared. Notice here, this is j is from 1 to p. I don't have beta 0. Okay, we don't have beta 0 be included there because when you penalize, you don't penalize intercept. Okay, you only penalize the parameter coefficients. This regression, if you look at it, okay, is the same. Is the optimization problem above is equivalent to the problem in the below, which is want to minimize the sum square error SSE subject to your the beta j square summation beta j square is less than equal to some like constant. Okay, this is actually the same. These two are the same, right? Because if you look at it, the above the form above is almost the Lagrangian Lagrangian function of the problem in the below, right? So therefore, in terms of this is the equivalence. Okay, these two problems are almost the same. Now, when the s is the s value is going to be corresponding to different lambda value. Okay, so that's these two things are so like if you have a larger lambda, you can have the smaller s. Right? If you have smaller s, then you're going to have or you have smaller lambda, then you're going to have larger s. Okay, in the cases where lambda equal to 0. Right, when in the case of lambda equal to 0, that means basically when the lambda equal to 0, you don't have any penalty term at all. So which means you don't have any constraint down below, then the s is going to be equal to infinity. But these two are the other forms. So if you look at this is if you look at the form in down below, you can see this is just the constraint optimization, right? Just constraint optimization. So the constraint is going to be this beta j squared. If you look in the two-dimensional space, it's just a circle, right? So that means your feasible region is a circle around the region. And then what it does is, if you have in a smaller s, that means the circle is going to become smaller and smaller. When the s equal to 0, that means you're going to only having one the feasible point at the origin. So therefore, that's going to be a minimum point. So this is when the s is smaller, becomes smaller and smaller, which means the constraint become harder and harder. That means when the s becomes smaller and smaller, the samely is just saying where the lambda becomes like bigger and bigger, right? Lambda becomes bigger and bigger because you want to minimize it. Say in the case lambda equal to infinity, right? In the case of lambda equal to infinity, in that case, your solution for the ridge solution, there's only one point, which is every beta has to be 0. Right? As long as beta is not 0, then this whole thing is going to be infinity. So when the lambda equal to infinity, then it's going to be equivalent to in the below, it will be your constraint s is going to be 0, right? So these are the same. This concept, okay, this concept is actually can be we're gonna see it again in SVM. This concept is called, this can also be seen, this S, okay, is kind of like all barging, okay? You can also be the so-called barging. Barging means you have certain barging, which is the S, which is the upbound constraint for all the beta. Then what do you try to do? You try to span this barging, okay? Some kind of like you want to span this barging somehow to each of beta, because each of beta is going to contribute to the budget, and you want to like spread the budget to the betas, beta j's, and try to making the beta j to be the minimize this SSE. Okay, so that's this concept. You can view it another way. This S is called budget variable, which is going to in the SVM we're going to see this is the concept again. But from the mathematical, the equivalence, you can see the ridge regression above is essentially is a constraint the minimization to below, right? This is the same. Now I just explain a little bit intuition what this is what the lambda, different lambda, what's the effect which correspond to what kind of effect. So this is just give you intuitively, okay? Intuitively, you can see when the lambda, when the penalty, the more penalization you gave to the target function, then it actually going to making your beta become more and closer to 0, right, to the origin. Because in the case of lambda equal to infinity, the solution is going to be the origin. Okay, so therefore, when the lambda is big, what it does, like I said, if it's a circle, then essentially it will goes more and more toward to the origin. That's the shrinkage effect, right? This is a shrinkage effect. You're going to see some like a graph in a few slides to see the effect. Okay, so this is intuition from that. Let's see how the ridge regression actually looks like. Okay, so because every intuition you can back it up within the the strict mathematical duration. Okay, so let's see in terms of the math. Okay, so how this is going to work out. If we're given a lambda, okay, given the lambda is called the penalty parameter. It controls how much penalty you want to impose to your target function. So let's say given lambda, okay? So let's given lambda, chosen lambda. Then this is our target function, right? I want to minimize. You can do the derivative by yourself. Okay, I'm not gonna go through. It's pretty simple. If you just do the derivative of the RSS with respect to beta, okay, it's very easy for you to see the ridge regression, the beta hat from the ridge regression. It will be x transpose x plus lambda I is identity matrix, right? With a column with a diagonal the column of 1. So this is going to be inverse of the x transpose x plus lambda I times x transpose 1. Okay. So if you look at it, this is from the regular regression, right? Regular regression beta had. Let me put in on that. The OLS, right? The regular regression. Regular regression, what is it? It's x transpose x, x inverse x transpose y. So what it does here is just having extra term, which you have in the lambda I including in there, right? So this is like I said, this extra term can making this x transpose x plus lambda I can making this variable to become basically is long singular, right? Become long singular. Because if your x are if some of column x they are correlated like a has a collinear, then this is x transpose x could be singular, right? Could be singular. Then therefore there's when taking the inverse, you know, having sort of like a yield condition. But once you're adding up, this is a term lambda I, which is full rank and invertible, right? Once you're adding this is some value of lambda I in there to making this is to actually to be invertible. So that's originally there's people do that for the purpose of the stability, numerical stability. Now let's look at this form a little bit, right? Your x, if we apply the single value decomposition to the x, then the x can be written as u dp. Okay, u is n by p vector, d is a p by p diagonal the matrix, and the v is a p by p the matrix. Now we also know this is a u and v, since it's a single value decomposition. We know u and v, these are orthogonal matrices as well. Now we can make an x to be u and v to be orthogonal. And the D is a diagonal matrix with a diagonal entry with D1 at bigger than D2. These are our eigenvalues, right? These are eigenvalues. We can order them in the sequence. Because the P, the reason we have P here, this is what I will assume this is a X is a full column matrix. Okay. So therefore the rank of the X is gonna be P. So therefore then this can be run as when U and P are orthogonal matrix, that basically means, since our orthogonal matrix, that means U transpose U is going to be equal to identity, right? That means your, because it's orthogonal, so therefore the U transpose is actually equal to the, well, it's basically it's U transpose U equal to identity matrix, and the V transpose V is also equal to identity, right? This is a definition for the orthogonal matrix. So if you plug this is a SVD, the single value decomposition of X, to the rigid solution. So what you have here is going to be, so X transpose is become VDU transpose. So this part, this is your X transpose times X, which is UDV transpose, right? Plus lambda I. Now I can write in as well. This is a V transpose. This is equal to this, and also V times V transpose is also equal to identity, right? Because they are this is orthogonal. So therefore you can write in this is your I times V transpose. So this is inside here we just apply the single value decomposition. X transpose becomes V du transpose. Now look at the first term, because U is orthogonal, so U transpose U equal to identity. So this is gone, right? This is gone. inside here, now it's become V times D squared, right? D is a diagonal matrix, so the D times D just be D squared. D squared just means for the each diagonal elements, we take the square of it, plus this is a lambda I, right, times V transpose. Because you having once this is gone, then both terms you kind of have a V up front and a V transpose in at the end, and then so you merge them, you're gonna equal this one, right? So the first term is gonna take the inverse of it, okay? Take the inverse of it. Now this inverse is just become equal to V transpose inverse times the middle part D. Then this is a D square plus I lambda I inverse times the V inverse, right? Times the V inverse, because V is square matrix. Remember, V is a square matrix. So therefore, V transpose is going to be equal to V inverse, right? Inverse of the V, because V is orthogonal, and U transpose V equal to I, so therefore V transpose actually equal to V inverse, right? So this is true as well. So therefore V transpose inverse is actually equal to V, right? Back to itself. Your V transpose is going to be V inverse. Inverse is back to itself. V inverse, that's just equal to the V inverse, that's just equal to V transpose, right? This is just V transpose. Now, in the V inverse times V times D U transpose Y. Okay. Now, if you look at this, is a V transpose inverse become V, then D squared plus lambda I inverse is going to move down. V inverse V, this is become identity, so you can drop out. So then what is left is D U transpose U. Right? So when you do this is a single value decomposition, what you have, ridge graph become the form down below. Now, the inverse of this is a D squared plus lambda I is very easy to do, because D is a diagonal matrix, right? I is also a diagonal matrix. So this D squared plus lambda I, essentially this matrix is going to be D1 squared plus lambda for the first diagonal, and then for the diagonal I will dj squared plus lambda all the way. Other matrix just 0. So this is the middle part is also a diagonal matrix, right? So the diagonal matrix, then the inverse of diagonal matrix just become the for each diagonal elements taking the reciprocal, right? So that's inverse. So therefore, this inverse of this matrix is very easy to do, right? It's very easy to do. So therefore, we can see, well, from here you still is not clearly to see what ridge regression actually does, okay? But let's see but from here we can see, right? You can see the ridge regression up to this form. This is clear, right? Now, if you want to do the estimation of the y, essentially that's x beta, right? X beta, that's the estimation for the y. So if you're using x times the ridge beta estimation, so that's become, so the above in the back, like what I highlight, there's the beta hat ridge. X is UD V transpose, right? UD V transpose. If you see from this term, basically U V transpose V, this is gone. Okay, this has become identity, right? So this we can drop it out, and then what you have here is just become U times D times this is this guy in the middle part, and U transpose Y. Okay, U transpose Y. Now U can be written, if you write it as a U as a column. So if you write in the U as a U1, U2 up to UP, okay? This will be the U is the n by p vector, right? So if you can write in this, the U can be written in this form. Now the middle part, remember this V is gone. D squared plus lambda I, this is a diagonal matrix. D is a diagonal matrix, and this D is also a diagonal matrix. So this matrix multiplication is actually also very, very simple, right? So this matrix is essentially become a diagonal matrix with an entry going to be dj squared over dj plus lambda, dj squared plus lambda, right? So it's going to become a diagonal matrix and other elements just be zero, okay? So if you plug in, this is a u, if you write in as a u1 up to up in this column vector, and then the u transpose. So this term in the above, okay, in the above, essentially can be written as summation j from 1 to p uj. Now uj is a vector, okay, is a vector times the dj square over dj square plus lambda plus uj transpose 1. Okay, so what it does is essentially this become the summation like this. Now uj is a column vector. Okay, uj is column vector. Uj transpose is a row vector. Okay, so dj square dj, this is a scalar. This guy over here is an n by n vector or n by n matrix. Okay, is n by n matrix. Y is n by 1, right? Y is n by 1 the vector, right? So this, therefore for each of j, okay, you will have your n by 1 vector and you sum each one of them. Okay, so this is what it does. But for each elements, we're gonna scale it within dj square over dj square plus lambda. Compared to the least square estimation, okay, compare least square estimation. Least square estimation, as I said before, essentially least square estimation is just treating lambda equal to 0, right? Because for the least square estimation, when lambda equal to 0, we don't have any penalty, then it's become the least square estimation, okay? So then the least square, when the lambda equal to 0, this become least square, which is just, then if lambda is 0, this is the middle part is gone, okay? Then it's become summation of uj times uj transpose 1. This will be the least square. Now if you compare the rigid estimation versus the least square estimation or the ordinary least square estimation, okay, you can see it actually shrink every component in here. Every component is actually making less, right? Because lambda is bigger than 0, so therefore the term right here is a term bigger than 0, less than 1, right? Because they are all positive, so therefore bigger than 0 and is less than 1. So what it does here, so that's why beta, the ridge, actually shrinks, okay, shrinks the estimation toward to 0, but not to 0. Okay, because this shrinkage factor is between 0 and 1, so you're gonna be making it smaller, okay? You're gonna have in the estimation, or else we make it smaller, but it cannot be, not be 0, because this shrinkage factor is not exactly 0. If it's exactly 0, gonna make it to 0. Okay. All right, is this clear? Any question about this? Like this is shrinkage. Why the shrinkage? We talk about in the form, like we talk about in this form. If you transform to view this is a ridge regression as one constraint, right? With an important constraint to there, we say this basically we will having the feasible region will be a circle around the origin, and therefore you want to minimize it. Basically, you're gonna make it part to that circle, right? So that's a shrinkage. This is intuition, but this is a mathematical, like the derivation to see indeed. Okay, we see the shrinkage effect from the math formula. Okay, so this is shrinkage. Question? Is this clear? All right. So for the lasso regression, so that's ridge, right? Ridge is easy to understand. Now lasso regression, lasso is stand for least absolute shrinkage and the selection operator. It's a long name, okay, but it's in fact it's just very simple. the only thing different, oh, I have a typo here. This is not ridge anymore, right? Of course, this should be, so this should be lasso, right? This should be lasso, okay? This is not the ridge. This is a lasso estimation. So compared to the ridge, the lasso estimation, you can see still we're gonna minimize the SSE. The only thing is the constraint is gonna different. Okay, constraint is gonna different. That's beta j. J here. For the ridge, gonna be summation beta j squared is less than or equal to some constraint, right? But in the lasso, what do we do is we summation absolute value of beta is less than or equal to some constraint. Okay, so the difference, only difference is one is the square, another one is absolute value. This will also the same argument. This is lasso regression. It can be seen the minimized summation of the SSE plus lambda times the beta j summation of the beta j absolute value. Okay, this two, and either you can put a constraint there, or you can add a penalty term to there. These equivalent each other, just like for the ridge regression does. So for the lasso regression, by making this is a smaller change, I change the penalty from the square term to the absolute term. It actually making the whole thing become very hard to solve, because for the ridge regression we can have a closed form solution, because the beta transpose beta, we can apply the derivative in there because it's a smooth function. Now, but if you have this is a beta j squared, okay, then this is not a smooth function anymore. Therefore, we cannot really apply the just apply the first order derivative set equal to 0 and solve it. So the ridge regression actually we do not have a closed form, okay, because of the absolute value in the penalty. This can be done using a technique called subgradient, or they are actually, but now people has ways to deal with it. Okay? We're not going to go through the algorithm to how to solve this, but if you're interested, you can check in for some numerical algorithm for things like subgradient or some other technique. We can actually this problem can be solved. Okay, it's not that hard, but just we don't have a closed form solution anymore. Now, what lasso does? Okay, what lasso does? Essentially, let's look at this term first. So for the ridge regression on the right hand side, okay, we have in the constraint is summation of beta j squared less than or equal to 0. So our constraint, the feasible region, gonna be a circle around origin, right? Your loss function or the error function, right? The error function is equal to y minus x beta transpose times y minus x beta, right, is equal to this thing. This function, okay, this function is actually defined as a shape geometrically in terms of beta is an ellipsoid, okay, is an ellipsoid function, which is given like above. So, and this function, if without constraint, it will having a global minimum like beta hat, right? This is a beta hat. This is LS. This is your ordinary square, which is x transpose x inverse x transpose y. Is given by here, right? Is given here. Now we have talked about. Remember, we talked about the optimization. We talked about like the constraint. And all this is where things, I think it will be easy for you, right? Because if I don't do that optimization, the lecture like one class, if I direct jump here, it's probably a little bit harder for you to follow. But now with given the constraint, the optimization, now it's very easy for you to see the minimum is going to happen at the surface, right? So if your circle is large enough, including this is a beta hat, then this feasible region is inactive. So therefore, it doesn't play. But if this constraint does not including this is small, then you know your optimization point is going to at the surface, which is where the ellipsoid shape of the SSE touch contingent within your circle, right? That's the point you're gonna have in this point right here. Okay, this will be your beta hat, This is our beta hat ridge. Okay, this is our beta hat ridge is right here. Is this point right here. So compared to the beta, okay, you can see it actually shrinks, right? This is the beta hat ridge is going to be closer to the origin, right? They're close to the origin. And that's this is the so-called shrinkage effect. But this beta, unlikely any of the beta, each one of beta is going to be zero, because you're going to touch the surface of this ellipsoid, right? So therefore, this is where shrink. And if without is in, if the constraint is inactive, it's just be self, right? So either it's going to be the self, be the least square estimation, or it's going to be shrink. Okay, so this is ridge. For the lasso regression, see, we only have two constraints, okay, two parameters, like beta 1 square plus beta 2 square is less than some square, like say less than 1. Then this is defined as this is going to be equal to beta 1 plus beta 2 less than 1, beta 1 minus beta 2 less than 1, negative beta 1 plus beta 2 less than 1, negative beta 1, negative beta 2 less than 1, right? So essentially this shape here is defined as a diamond, right? It's defined as diamond shape is given there. So the constraint, the feasible region for the ridge is this diamond shape. And this is the shape or the contour for your SRC is still the same. It's still the same ellipsoid, right? But now when you see when this ellipsoid expands, when it touches, okay, when it touches the diamond, there is some chance, okay, there's some chance. Then the ellipsoid can touch the diamond exactly at this vertex, right? Because it's irregular, right? There are some vertices stick out. It could touch the surface right here as well. Okay, it could touch the surface right here. But there's a good chance it can touch the vertex. When it touches the vertex, okay, when it touches the vertex, for example, like here, this is beta 1, this is beta 2. When it touches the vertex, what does it mean? That means this point basically is our beta lasso, right? This is our beta lasso. So at this point, your beta 1 will be exactly 0. Okay, this is beta 1 will be exactly 0, because this is if you touch the vertex always happen at the axis, right? At axis, either this is in this case is on the here. When it happen to this point, that means your beta 1 is basically just 0. Okay, the beta 2 is going to be shrink. The beta 2 becomes smaller. So the lasso regression, what it does is sometimes it can shrink your certain parameter down to 0 exactly. Okay, for some other parameter, it will be just shrink. So this is a slight difference in there. So if you're using lasso regression, you can actually, if you apply some of the parameter will become exactly 0. Now, when your parameter becomes exactly 0, what does it mean? That means that that coefficient x will not contribute to your regression, right? Will not contribute to regression. So if x is not contributing to your model, to regression, that is similar to a model selection problem, right? Because your model selection, say you having a certain variable y regress from x1 up to xp, you say you are not sure, you know this x1, xp is given to you, right? Given to you. But it's possible in practice, not all the axes, not all the columns are significant or important. Okay, so some of them may be just noise. It doesn't contribute to y at all. So therefore, in practice, you will have a step called model selection. Okay, you all have one step is called model selection, and that model selection basically called model selection. That model selection it means we want to select in from the given set of your the features or the covariates. We want to select a subset, okay, which are important to your regression, okay, only contributing regression. And then if you say my model selecting, I only determine x1 up to xq, okay? Q is less than p. Only define, like, first q variables are significant. So basically we leaving another subset of x, leave it out. Leaving it out essentially is the same effect we see the effect for this set of the parameters leave out. They are saying their beta equal to 0, right? Their coefficient equal to 0 is the same. So if you can make a coefficient equal to 0, then in essence, what you're doing right now is actually doing a model selection, right? So it's actually doing model selection. So therefore, the lasso actually has a property of model selection, okay? In most cases, like ridge, there's a model estimation. You given a set of the x, you try to estimate what is the coefficient. That's a model estimation. Model estimation is not the same as model selection. Okay, so then this lasso actually can sort of like using like a one stone two birds type of scenario. You can do the model estimation at the same time. You can also do some kind of model selection. Okay, so that's which is a good property. Model selection, I mean, this itself is a big topic. Okay, I'm not gonna dive into that too much. But I just want to point out is when you do this is you do have this is so-called if you're making your x to be coefficient to 0, that's you essentially are doing the selection problem. Now let's look back. Okay. We can see the penalty. Okay, you can see the penalty. We can. This is if this is to be the 1. Okay, if this is to be order 1, this is we are doing this is lasso regression. If the order of 2, okay, that's ridge regression. But can we making this arbitrary order of q? Right. So if you're making the arbitrary order of q, then the constraint the shape of constraint actually become like this. So if you can see, if it's 1, this will be a diamond shape, right? This is your lasso, the fixed region. If it's 2, it's gonna be the circle. Okay. Now if it's less than 1, okay, if the order is less than 1, then you can see it actually become it's gonna be the curve is gonna become inside, right? It's not a convex anymore. It's actually your set become like concave, right? It's not convex set anymore, right? Because if you convex, if you point like 2 points, if you make a line, it's still in the set. If the q is less than 1, this is not convex anymore, which means this is gonna making your vertex like stand out more, okay? Vertex like more. If you're making this is q even larger, say q equal to 10, it's become more like a square, okay? It's gonna become more like a more square. So depends on what you're gonna do. So if your q is equal to 0.5, like if the shape is like this shape, right? You can see when you do the shrinkage, you will not be able to touch the surface anymore, because surface will be hiding. In order to touch this surface, you have to touch one of the vertex first, right? Most likely. So therefore, if you do that, then it will be sum of the beta. Okay, will be 0, because once you touch the vertex, that means you want the sum of beta is gonna be 0. So in practice, okay, with all this is in theory we can choose like different q values to solve, but in practice the lasso and the ridge are like two most popular ones, because others is more or less giving the same property, but within say for example q equal 0.5, okay. This is gonna making the problem is even harder to solve, because now you have the square of the absolute value, right? That's this is gonna making to solve that problem is it become even harder. So usually then people are most likely just either you using lasso or ridge for the regression problem. The ridge also is calling this is sort of solve the thresholding the problem. This is just basically saying if you're plotting out, okay, if you're plotting out your ordinary square beta versus lasso beta, say given for a given problem, okay, for a given regression, if you're plotting out within the lambda, using given lambda, So what it does is basically when the lambda is when the lambda is small, okay, when the lambda is small, when the penalty is small, you basically just have a shrinkage, okay. So you can see this line right here. This is representing your beta, the ordinary square. So you can see for the lasso regression, it's gonna be just do a shrinkage, okay. And this shrinkage is gonna keep going, and keep going down as the lambda increases, okay. So the shrinkage is gonna keep going down until it reaches some point. This is going to be this particular beta, it will be shrink to 0. Okay, it's going to be shrink to 0, and then it will stay on the 0 until then once you reach the 0, then further increase in lambda, it will change a little bit more because the penalty is already large enough to make this beta to be 0. This is if the beta is on positive side. If the beta on the negative side, then you're gonna do see from other side. Okay, so this is how it goes. So this is called soft threshold. Okay, we're gonna have in this means threshold means when it reach the certain threshold, then you have value. Otherwise, it's gonna be 0. Okay, so that's this is the effect of the beta. This is another factor. This is a picture we adopted from the elements of statistics learning that they have using lasso regression to a regression problem. In this regression problem, you all have 9 covariates. Okay, this is only 1, 2, 3, 4, 5, 6, 7, 9 is corresponding to the 9 covariates. Now, each of the this is the y-axis. This is corresponding to different shrinkage factor. So shrinkage factor is not the same as lambda. Lambda is our penalty parameter. Okay. So shrinkage factor, this is just saying if equal to 1, that means we don't have any shrinkage. Okay. So when it's 0, we're gonna shrink to 0. So what it does see here is just basically just saying at a different shrinkage factor, a different penalty, different lambda, how the lambda is going to change. If you apply different lambda to the regression, and you can calculating a set of beta, right? Beta 1, beta 2 up to beta 9, and then if you plot them out over there, you can see how their trajectory going to change. So when the shrinkage factor equal to 1, this is your linear. This is a least square estimation. You can see if you draw a line, there's a vertical line. You can see this going to see this will be the estimate for x1, x2, x3, and 4, 5, 6, 7, right, and so on. So these are the coefficient corresponding to the least square. If you make a shrinkage a little bit, say to the 0.8, then it will shrink. You can see 9. This every single value, okay, it actually become a little smaller. Or for this particular one, it actually pretty robust. Okay, it doesn't shrink. It will almost stay the same. That means in that direction, we don't have much shrinkage. So for some direction, they're actually going to shrink. Let's just follow one of them. Let's see the line, okay, for the x9. So you can see as the shrinkage factor become stronger and stronger, which means shrinkage factor towards 0. You can see you're going to gradually go down until it reaches to the point almost close to 0. Shrinkage factor was 0, it will become 0. But for some others, okay, let's see for the beta 5, for the 5 factor, you can see it's going to become absolute value. Okay, it's negative, but its absolute value becomes smaller and smaller, shrink towards 0 until it reaches to a certain point, it becomes 0 and then stays 0 forever. Okay, so this graph basically just show you within the different the penalty, you can actually have different the parameter estimation. Okay, so each your beta actually gave you a different model, because if your coefficient are different, that means when you do the prediction, you will have a different value. Okay, they are related but different. Okay, by different model. Now here it is. This come to another question, right? So what is this lambda? How do you determine this lambda? Right? So because different lambda is going to give you different beta estimation. So beta actually is closely related to lambda, right? Depending on if your lambda is very large, which means a lot of shrinking you can make in every coefficient become all zero. Right? If every coefficient become all zero, that means you don't have anything. That means you don't need to make any prediction, right? So it's just making prediction of zero, which is useless. So we want to making this lambda to be somehow large, so we can penalize it. You can shrink it a little bit, but not too large, right? So this is the lambda in this case. Okay, lambda in this case, this is we have a term for it. It's called hyperparameter. Okay, it's a hyperparameter. It means if something is a parameter, it's not part of your model. Okay, it's not part of the beta, but it can determine your model. Okay, so it's called hyperparameter. Is a model, is a parameter actually is higher in the higher order of the model because your model is determined by this thing, right? But it's not part of the model. So the usual way to select in lambda is is a method people usually call cross validation. Okay, cross validation. That's this is another topic about how to do it. Briefly, okay. Briefly, what you can do is you can making your you can change your data training data further down, okay, to another toolset is training, and then separate data to a training and a validation set, okay, validation set. Now, what you're gonna do is you're gonna choose in your different lambda, okay. You can do like so-called grid search, choosing different this lambda to apply to the training data, okay. And then using this is so each lambda is gonna having a different model, and then using this lambda model to predict on the validation set to see which one actually giving the better validation error. So by using this cross validation, you can choosing this is a sort of making empirical choosing the one parameter with lambda, which is gonna be the best lambda. We know the lambda couldn't be, it will be somewhere in the middle, okay? Because lambda is if lambda, say if lambda equals 0, that's the least square, okay? If lambda is infinity, they're gonna making every estimate to be 0. We know that's also not optimal. So lambda will be somewhere in between, okay? Somewhere in between. So then within that, then you further has another test set called test set, okay? So then the test set is will be, once you have the lambda, you want to evaluate how good the model you apply your test data set. So training and the validation, these two are together. This is the whole thing is your training. Because this is a validation is meaning for determine your hyperparameter. Okay, so this is how in practice how it works. Okay, any question on this? Is yeah. Uh-huh. It's so lasso regression, this is actually can be corresponding to another, if you do that, this is corresponding to another method called stage-wise selection or stage-wise regression. Stage-wise regression, lasso regression is indeed one type of the can be corresponding to one type of so-called selection process. Right? Because for the model selection, there are different methods, right? You have like a forward selection, you have backward selection, you have this is sort of like the subset selection. They have this so-called stage-wise selection. So they have different values. Lasso regression is indeed corresponding to regression called stage-wise regression. In that stage-wise regression, what it does is when you're having, you're gonna starting with like a model with an intercept, okay? And then when you do the regression, you want to choose like forward selection. What it does, use forward selection. Basically, you feed in the model within like including one variable, x1 up to xp, right? One variable, and see which one give you the large improvement over the intercept. Okay, then that will be the first variable included in the model. That's the forward selection, right? Then given the one variable you write in the model, you search in the rest, say rest P minus one variable, say which one making the model like a better, most significant, right? So you do that. So that's forced selection. Stage-wise selection is a little different. What it does is say in the first set, you say you having this is a x1 up to xp, you do like a one regression within one variable, each one of them. Say xj is the most significant one, okay? Is that different from the forced selection? You can including the xj into the model as your first variable, like you put in there as a base. Now what it does, stage-wise does, you're going to include xj into the model within a little bit, within a small coefficient, okay? Say point like 0.01. You're just adding a little bit the xj effect into the model. Within that, you're going to search again. So at each step, you have in this variable into there. You're going to adding a little bit effect to the most significant the variable into the model. Then this is like a you're taking the small step, everyone. So then this lasso regression, you can prove it. Okay, exactly, people can prove that lasso regression is equivalent to that stage-wise the selection. Okay, so therefore in that sense, yes, lasso has in the ones lasso kind of like eliminated first would be the most like the least significant. Okay, so by the order, in the order of it can be eliminated to the model. It can kind of tell you which variables are more significant than others. In here, we don't talk about like cardinality issue. In that's another whole different things. See, in here, what I'm trying to here is try to introduce the method to you, and then how to use it. Okay, this is up to like later on when you learn more about other you can do some elimination at the beginning, right? You can do PCA, so like to get in like orthogonalism. So these are those topics that are all interconnected. It's not like this lasso can solve every problem. Okay, it's not. It's just like one method can solve some problem. Okay, so it depends. You don't view this as like this is like the best method. It's not. Okay, so you can combine this with other technique like in the future as well. All right. All right. Any other questions? All right. So if not, let's see how the lasso and the ridge within we can apply to big data. All right. So what we just introduced is the basic is for the small data. Now for the parallelized logistic regression, if we want to apply to big data, then we can similarly we can use the ADMM algorithm. Okay, so if we use xi, yi to determine the data in the ith partition, okay, beta j will be coefficient for the partition I. Beta is a consensus coefficient. Then the R beta it will be parallelized terms such as this is R beta and beta the square, right? Square the norm. So then the optimization problem. It will be we want to this is the problem we try to work with. We want to minimize summation of all the likelihood, summation of the negative log likelihood on all the data, right? So this is on all data, and then subject to beta I equal to beta. In addition to that, I have a penalty term called R beta. Okay, so now, one thing I want to mention here is your penalization, okay, is on the consensus parameter, not on the local parameter, okay. So therefore, you don't have J here because the first part right here, this is your negative log likelihood for whole data set, okay, for whole data set. This beta, therefore, your goal is try to find a beta. So your penalization is on the consensus beta, okay? Is on consensus beta, not on beta j. So this form right here is actually can be it actually can match the ADMM form very well, okay? Because now your target function can be separated into two components. One set is beta i's. This beta i's, this is one set of parameter. Beta is another set of parameter. used to be if we don't have this, we said G beta, G beta is implicit, right? Is constant equal to 0. But now the G beta is become R beta is a penalty term. Now is explicit, right? Subject to beta J beta I equal to beta. So this is our constraint. So the ADMM algorithm, if you're still remember from the previous classes on logistic regression, then the ADMM the algorithm is just like this. So for the shrink for the local estimation, okay, local estimation, it will be this guy right here. It will be for each local, you're gonna have a local likelihood function plus this is a plus this is a method multiplied term, which is you have in this is the L2 term, square of L2 term right here. So you all have in this is yeah, because in here you don't have R beta into there, right? Because for locally, this R beta it does not contributing to the local estimation, right? Because you don't local beta I has nothing to do with beta, okay? So therefore, in the local estimation, it will be exactly the same as the logistic regression. You don't. So you just having your UI, which is your Lagrange multiplier, and your beta, which is consensus. Once you have this to update it, then the locally is the same. The only thing is in the globally, okay. In used to be in the master node, we just collect the beta from the local beta I and take the average and then send it back, right? Now instead of that, now we have a small optimization need to do, okay? Need to do in here. So the optimization for the beta is actually, because if you look at the term right here, it actually going to have in the R beta, and you also have in the Lagrangian the terms here, right? So then this is when you do the optimization, then the beta used to be, if you don't have this R beta term, like I mentioned before, this is a beta. Beta essentially just equal to beta bar, right? Just beta bar. Now because you have this is a R beta here, then the beta is actually you're gonna minimize this term. You have to explicitly, okay, to work on this minimization term. So you're gonna be R beta plus 2 n times rho over 2 beta minus beta bar, and then this is this L2 term, square L2 term, and minimize this, give you a beta. And then once you have this beta, then you can update your U. U is equal to Y divided by the rho, right? The Lagrange multiplier divided by rho. So then this is you can update your well, once you have the beta, you send it back to local processor. Local processor is going to update your UI, each one, and then once you update UI, then you can update your beta, right, and then correspond iteratively. There is a little bit this term right here. Okay, now you can see the quadratic term you need to minimize is actually should be, if you just don't look at it, the quadratic term here actually you having a UI k, right? You actually having inside here should be, because you can see here you actually having your term is instead of beta minus beta k, you're having actual UI here. So your term right in the second term, okay, supposedly it should be R beta plus this is the n times rho. This is well, should be, it should not be n, should be summation of I from 1 to n. Okay, it should be minimize this term. Okay, it should be minimize this term. Now you can actually show. Okay, you can actually show. It's very easy for you to show. Minimize this function. This is equivalent to, okay, this is equivalent to minimize R beta is the same plus this is a rho over 2 summation I from 1 to n of beta minus beta bar, beta k. This is square. Exactly the same. Okay. This is based on the fact. This is based on the fact summation of UI is actually equal to 0. Yeah, because we showed before summation ui is equal to 0. If you're taking I'll leave the derivative to you, okay? If you're taking the derivative of this function, okay, if you're taking the derivative of this function, and then you're gonna say this actually become then this this derivative you can keep it. Then the second derivative become linear, okay? So therefore, in this becomes summation of beta minus beta bar plus uk. So therefore, since summation ui equal to 0, so then in the first order derivative, that's ui actually is gone. Okay, so therefore, if you take it back, root back, so then therefore the ui actually can be eliminated from your minimization. Okay, so you can verify this is by yourself. Is a very easy verification. I think this is a yeah. So then depends on, right? Depends on what your R beta is. So if your beta is lasso, then this beta is summation of beta j absolute value, right? If it's ridge, this R beta is summation of beta j squared, right? So depending on your penalty term, so then the complexity to apply ADMM to solve the penalized logistic regression will be almost the same, okay? Almost the same as you're solving logistic regression, because this part here is fast, right? This part is here is fast. This is a small problem. This is just having like a you just have like n beta j's, and you try to minimize this problem. So this problem is a small problem compared to the computation in here. This is nothing, right? So therefore, in the ADMM, so if you want to do penalized regression, okay, in terms of computing time, it actually doesn't increase a lot. Okay, so this is for the penalized logistic regression on also for the penalized the regression problem. So any questions on this? All right. Any question from on the Zoom side? All right. So if you guys don't have any question, then I'm gonna continue. I'm gonna get started with in the support vector machine. I'm a little bit running out of time, okay, because I have two SVM and random forest to cover. I'm having including then after today I have 3 lectures, okay, so I'm a little bit I may not be able to cover everything, but I'll try the best. I may have to speed up a little bit. So SVM, some of you probably have heard it before. Okay, SVM is one of the best methods, so like off-the-shelf method for people to use, and it has I'll show you why. Okay, because it has SVM has a very good intuition behind it. Okay, to show this is a good method. But first, let's just give you some overview. Okay, SVM stands for support vector machine, is a system for efficient training linear learning machines. Okay, in kernel including feature space. You probably haven't. This is some of the term that may not make sense to you. Okay, but don't worry, we will go through each one of them one by one. Like say, what is the kernel induced features? Right? What is the linear learning machine? This may not be, like I said, if it doesn't make sense to you, it's okay. I'll explain later. I want to just give you high level. Okay, at the beginning, give you high level the SVM overview first. SVM pick the best separating hyperplane according to some criteria. Okay, see, in this case, it's called max margin. And the training process essentially is just optimization process. Okay, and the training set is effectively reduced to a relatively small number of the support vectors. So the training set for the SVM, the model is mainly depending on a few important points. Okay, those are few important points. We call it support vectors. That's why we call support vector machine. So let me in the last 5 minutes, let me give you like some intuition behind the SVM. Okay, so the next class, we can dive into the math. So what the decision problem, okay, we can roughly view it as y is a binary outcome, -1 and 1. In the logistic, we use 0, 1, right? It doesn't matter. It just means y can only have two values. In this case, in the SVM, we use -1 and 1, okay? This is it's the same. So then we want to find some function of x. X is your features, right? Some function of x, which can transfer. So fx maps your x to a real line. So fx become a real value. Then if fx is bigger than 0, we see yi equal to 1. If fx is less than 0, we want y equal to -1. So basically, the sign of the fx determine the prediction of the y, to which group it's going to be. Is it become one group or -1 group, right? You for all the classification, the binary classification problem, binary classification, then this is the problem, right? This is a problem, okay? Now, the linear separator is saying, linear separator classification can be viewed as a task with separating the class in the feature space by constructing linear combinations, right? So supposing here we have two features, x1, x2. So then each dot, okay, each dot then can be representing each dot representing a group. Blue is like -1, red is +1, right? So the color of the dots represent the group this each subject or each dot is in. And then the x1, x2 is the corresponding features. If you plot it now, you can see in this case, for the red dots is beta transpose x plus b bigger than 0, beta transpose b plus less than this for the blue dots. So if we can find some line or hyperplane, beta transpose x plus b equal to 0, this is a hyperplane, right? Can be separating this two. And if we're taking sign of this, then this beta x plus b can perfectly separate these two classes, right? Can perfectly separate. This is a linear separator. So we are taking this in a linear form. Now the question is, for these two group of objects, there could be many linear lines to separate these two groups. Okay, so you can be this is the line I draw on the slides is one. If I just let's assume this is the line, right? The line I draw here like this one could be another one, and this one could be another one, right? I can draw infinitely the lines which can separate these two groups. So in other words, the linear separator, okay, for this particular example is not unique. Okay. Now then here comes the question: is there a linear separator that is best, okay, or is optimal? Is there does exist, right? A linear separator which we can see is the best separator. Okay, it's better than any others. Okay, so intuitively, what do you think? What kind of line I draw here will making the best separator? Is what? Y equal to, you mean like this? Yeah. Well, in this particular, this may not be the best one, but you are in the right direction, right? This line, if I draw this is called line 1, this is line 2. Intuitively, you will see line 1 is better than line 2, right? Because it's somehow you feel line 1 separates two classes better than line 2. So what is the intuition behind it? The intuition behind it is basically, so this is not the best separator, right? It's kind of not, and this one looks better, okay? So intuitively, what we are trying to see here is we basically try to find the closest point being so-called, this is the convex hull. Convex hull is, suppose you have two groups. If you connecting the group, like you can form like the outer, this is a hull, right? If you're connecting the outer space of this is all the training point. If you're connecting them into this is a convex hull, and if you can find like in between this is two regions, if you can find something which is kind of like making this is a true distance to be largest. This would be your best sapling line. In these cases, you see the C and D are the closest 2 points from these 2 groups, right? Now, if you're making a line between C and D, and then you draw a line the perpendicular to this C to D, then this line, if it's somewhere in the middle, this seems to be the best sapling line. Okay, so then this is going to convert into this is intuition. Okay, so in the next class we're going to convert all this into mathematics, into the math thing in classifying the so-called margin. Right, then we can form that is based on the margin concept. We can formulate actually a concrete optimization problem, and then we solve it. Okay. All right, so that's for the next class. We're gonna see details about SVM. This is all for today. I'll see you guys next week.